I turn it on? Yeah.
If you're hungry, you hear it.
Yeah.
Okay, so I'm still under the weather, but I'm much better than I was last time. So I'm gonna start out by going over more carefully the derivation of the action for a gauge theory on a lattice. I think I finally derived this in a way that's optimal. So I'll try to show you that. Thanks for doing the boards for me. The basic quantity, of course, is a Wilson loop, and it's important to say that this is a path-ordered exponential of an integral around the loop of the gauge fields like that. These gauge fields have basically, in other words, AI has a generator in it, T sub A, and it's an A sub AI, and I think it has a coupling constant, and it has also a factor of I. I haven't it's a matter of convention whether you have an I, a minus I, and whether you include the coupling constant. So let's just say that it is whatever we need in order that that A j comma I minus AI comma j plus AI comma aj should be F ij, where this is the Faraday tensor for the non-abelian gauge field. And this, of course, is going to give you something quadratic in the gauge fields and linear in the generators.
Sorry,
Yeah.
real quick, can you remind me, what does the general gauge transformation on this general gauge field look like?
Okay, sure. AI prime, and I might as well put in of x because this is a local gauge theory, and it will be u of x, AI of x, u inverse of x, minus di u of x, u inverse of x. And because u inverse is 1, if you differentiate that with respect to xi, you see that you could equally have written this as u of x di of u inverse of x. So this is an alternative expression. So it's not that you put both together, it's one or the other. So I don't know, you guys have a gate that's an and or gate or something? Okay, so what I want to do is to show you that this is in fact e to the, let us say this is Fij dx dxj. I think this is a little bit misleading, so let me be more explicit. Let's suppose this loop is in the xy plane, two spatial directions, say. Then this is xy dx dy. If I put the ij in there, then we're going to, it would still be correct, but it would be, I'd have to introduce at least the 1/2. So what it really is the integral of this around the perimeter of the loop is equal to the integral of the Faraday tensor over the surface of the loop. And this is in the limit of dx going to 0, dy going to 0. So that's how I'm going to analyze this. And the basis for my discussion will be the Baker-Campbell-Hausdorff identity, which is e to the a plus b plus 1/2 the commutator of a with b, and then it's an infinite series. There's no closed form that I know of, although since Merman is still alive, we should stay tuned and he may work out a closed form version of this. I was once at a conference and I was on a boat, not a boat, a bus. And, you know, people were talking as they usually do. And behind me, I was just absentmindedly, inadvertently listening to the conversation. And I thought, gee, one of those guys is awfully intelligent. Turned out to be Merman.
Was he the one that was just in the news recently about?
Was he the one who won?
Was just in the news recently about solving some math problem that had not. What was this about? We talked about it in the other class. Austin, do you remember this?
No.
I don't remember. Okay, maybe I'm getting the names.
Why don't you send us all an email later?
I was just trying to remember who he was.
Merman was the co-author of the standard textbook on solid-state theory of condensed matter physics. He also, I guess in his spare time, worked out formulas for n factorial, and in fact his formulas are actually exact. And if you then do the leading approximation to his formulas, you get remarkably accurate formulas. So the history of the n factorial formulas is that the first one was due to somebody in England or Scotland or somewhere up there. What's his name? In fact, it's
Sterling.
Sterling. And then there was an Indian mathematician who was self-taught. Does anybody remember his name? I'm terrible.
Was that Ramanujan?
Huh?
Ramanujan?
Yes, yes. And he came up with a formula which in my eyes is totally bizarre. Although, frankly, the Stirling formula is bizarre also. Although there's a nice derivation involving the method of steepest descent that does that. But I don't know how Ramanujan, if that's his name, derived his formula. And then Merman apparently somehow found the exact formula and then wrote down approximations, which are, and it's remarkably how much better those formulas are than Stirling's. In fact, I have a figure in my book where I plot the error, and there's no room in the graph to put the error of Stirling's formula. It's way off, you know, the ceiling somewhere. surface of the moon, whereas the Ramanujan and the Merman things are sort of close to each other. In any event, there's one more term here, which is 1 over 12, b comma a. And then there are infinitely many terms. Of course, when AB is itself simply a complex number or multiple of the identity, or more generally, something that commutes with both A and B, all those terms vanish and you just have Glauber's identity, which is useful out of optics. So, what I'm going to do then is I'm going to apply this in the limit in which dx and dy go to 0 and apply it to the Wilson loop. And I'm going to write this Wilson loop as e to the a sub x dx. And a sub x means a in the x direction. And the next one is e to the a sub y dy. And let me draw a picture here. So this is a sub x, and this distance here is dx. And then over here we have a sub y. But here we have a sub y plus a sub y comma x, in other words, the x derivative of a sub y times dx. And up here, we have a sub x plus the y derivative of ax times dy. But now this is an ordered path integral, and it's ordered like that. And so this term here is a sub y plus a sub y comma x dx dy. And this one has a minus sign in it, so it's e to the minus a sub x dx minus a sub x in the y direction dx dy. And this one is as simple as the first one. It's e to the minus ay dy. So it's the product of these four, and notice the way I've written it so as to make the path ordering explicit. By the way, in some of these, some applications of the Wilson loop, one has the matrices path ordered and the operators time ordered with respect to Euclidean or ordinary time.
Yeah, maybe.
Wait, I think I'll give you another candy. What?
Yeah, no, I'm just a little confused as to these terms and where they're coming from, and why do we have these like derivatives with respect to x of ay on one side, but not on the other side?
Okay, sure. Well, the point is that.
Oh, that's ay at the point x plus dx. Is that the idea?
Right. Yeah.
I gotcha.
Yeah. So to do this one, this is I'm taking this the field to be a here, and over here it's a plus the x derivative of a times dx, and up here it's a in the x direction, but up here it's that plus the y derivative times dy.
Yeah, just adding dy and dx
Yeah.
results.
Now, so I'm going to apply the identity to the first two, and in fact what I'm going to apply is actually Glauber's identity, because the extra terms due to Baker, Campbell, Hausdorff are of third order in the tiny for length of the square. And okay, And so this is going to be, well, actually, it can be e to the, because we have a blackboard here. So what we have then is a sub x dx plus a sub y dy, and then, so I'm doing these two terms, plus a sub y comma x dx dy. But we also have to put in the commutator of the two exponentials with a factor of a half. So this is plus a half commutator of ax dx with ay plus ay comma x dx dy. Okay, so all of that is in the exponential, and that's the product of the first two terms. And then this multiplies the product of the second two terms. And I now see that this might have been clearer if I had just used exponential notation. So let me write this exp, big parenthesis. And let me write this as exp, big parenthesis. So this is then minus a sub x dx, and then minus a y dy, and then this term minus ax comma y dx dy. And then we have to do a commutator of these two terms. And so this, and everybody's got a minus sign, so they cancel. And we have a sub x plus a sub x comma y, whoops. Y, this times dx, comma, a sub y dy, end of commutator, big parenthesis. Okay, so that's the first stage there.
Should that be a minus sign in front of the 1/2, or is that my misreading?
No, because
Two minus signs.
you've got a minus sign here, a minus sign there, a minus sign there, right? And the formula is,
Factor.
so the two minus signs the minus signs cancel. It's, I'm always so happy when the minus signs go away, because minus signs give me the creeps. Somehow eyes, I prefer eyes, I don't know why. Anyway, well, the rest of this really falls apart, because you can see that the next step is to take the exponential, where you take this plus the commutator. Or when you do this plus this, you can see that this term and this term are canceled by that term and that term. And what you have left is the x derivative of, in other words, this thing is exp of, and it's going to be ay comma x minus ax comma y dx dy, and then if we take the sum of these two terms, well, what do we have? Well, we have a couple of terms. One is we have the commutator of ax with ay, and that is times dx dy, and it comes in twice. So this is plus simply the commutator of ax with ay dx dy. This extra term here, we can just ignore because it's a third order in the smallness. And the same thing with this extra term. And also, we don't want to bother commuting these terms, which are of second and third order, with these terms up here, which are first or second order, because the lowest order would be third order. So the remaining term is the commutator simply of these two terms with these two terms. But that's zero because they are the same term apart from a minus sign. And so altogether we have this, and this is then just e to the fxy dx dy. So that's a very nice result, and it's I guess it's true of the line integral around a closed, the exponential of the line integral around a closed loop of anything. I mean, we haven't used that these a's are of the form a's of ATA. We haven't used that. And so what we get is this expression in an extraordinarily general context. And that means that the mathematicians must have chewed this over and spat it out several times. But I don't know. I looked in the literature trying to find a nice derivation of this, and I don't know, I didn't find anything simple. But on the other hand, I was pretty sick when I was looking in the literature. I was at the conference, by the way, the APS meeting in Denver. I don't know. I don't think I learned. I mean, I must have learned something. I hope I learned something, but the main event was, you know, the announcement of the imaging of the black hole, but that was already covered by the popular press. So I skipped that talk and went to something else. All right, now let's see, what do lattice gauge theorists do with this? Well, you want an action, you want a nice way of writing the action of the gauge field on the lattice. And so what you can do is you can take this Wilson loop, and the Wilson loop, of course, is an exponential of a matrix, and so this is itself a matrix. If you want a number, then you have to trace the Wilson loop, and so you take the trace of the Wilson loop, and or equivalently, you just take the trace of the Wilson loop minus 1. In other words, you subtract out the identity matrix, so that if the Wilson loop was in fact just the identity, then you get 0. And so the action for a general lattice gauge theory is of this form, namely trace of the Wilson loop minus 1. And if we look at what that is, well, that's trace of e to the f, let us say, xy, dx dy, and minus 1. And so now if we expand this, because this is a hyper-small quantity, what we get is 1 plus fxy dx dy plus a half fxy squared dx squared dy squared plus all sorts of other terms. and then minus 1. And so the first term cancels, and we're left with trace of fxy dx dy plus a half fxy dx dy squared. Now, in most cases, we're studying gauge theories of groups that are defined to be groups of matrices with determinant 1, and so the generators are traceless. So the trace of all the generators of each of the generators is 0 for SON and SUN, and there's that other gauge group that I keep telling people that they should pay attention to because no one else does. The what is it called? It's getting so I can't remember the name of anything anymore.
Exceptional Lie
Huh?
groups? Is it one of the exceptional Lie groups, or is it like the symplectic?
Just the standard Lie groups, not the exceptional ones.
Symplectic.
Yeah, you're talking about the
The what?
symplectic groups?
Yes, the symplectic group. And so that would be SP2N. Now, whether they're generators or traces, I actually don't remember. So I'm going to put a question mark there. But as I said, everybody ignores the symplectic group. And when Cartan worked out the Lie algebras and the structures and some of the representations of compact Lie groups and discovered the exceptional Lie groups, he distinguished between SO2N and SO2N plus 1 because the structures are different.
I think the generators of like SP2N are quadratic things in creation and annihilation operators.
Okay, so does that mean they're traceless?
No, so you have number operators, right? You can have A dagger A.
Really?
Mm-hmm.
All right, let me check that.
And it does rotation.
All right, I'm surprised, but you're probably right. Okay, so what happens then is that this term goes away for all the groups that are basically considered SON, SUN, and so this is just the trace of 1/2 the trace of fxy, say, squared times dx dy squared. So it's the square of the area. And so when one does lattice gauge theory, then, of course, what you get when you take the trace is this fxy is fa xy ta, right? And the trace of ta tb is k delta ab, where k is the constant that's associated with whatever representation the t's are in, depending on the group. And so to finish this, the trace of the Wilson loop minus 1 is 1/2. It will be k over 2 fa squared xy dx dy squared. So now if you want to get a physical action in Euclidean space, what you want is you want to sum over all 4 values of x and y, and of course when they're both equal, it's 0. And so what one said, that Wilson action then is k over 4 ij squared, and here we make dx be the lattice spacing, so this is then a to the fourth. And so that's the expression. And or what I should say is let's all right, I've gotten things a little bit backwards here. So if we take the trace here, this is going to be K, and we're going to get a sum over all the generators. The actual action that we want, which would be SW, would be simply a quarter FA squared IJ a to the fourth. And so this would be the trace of the Wilson loop minus 1, and we have to divide by 2K. Or do I have that wrong? We certainly have to divide by K to cancel the K. We'd like to have a 1/4. The extra factor of 2 is because one sums over all I and J, and so you double count, so you put in an extra 2. But here, what is happening is this Wilson loop, when I worked it out, I just picked 2 directions, X and Y. Here, what one does is one sums over all possible plaquettes or small squares in the lattice. So you do, for example, that plaquette, and then you do this plaquette, and then you do this plaquette over here, and then you do the ones that are on top, and then you do, so if we were in 3 dimensions, you would have altogether 6 plaquettes. If you're in 4 dimensions, you have, I don't know, is it 8? Or I haven't worked this out in a while. Anyway, so however many squares you have, that's the many, that's, in fact, it must be 4 times 3 divided by 2, that's 6, that's 4.
Like 2-dimensional faces, or is it?
How many 2-dimensional faces of a 4-dimensional cube? And so I was saying, you have an I and a J, and they can't be the same, so you divide by.
So the faces of
So
a
it's 4
4-dimensional
times.
cube are 3-dimensional, right?
Huh?
The faces of a 4-dimensional cube are 3-dimensional.
It has two-dimensional faces.
Well, all right.
2 faces too.
Cross out face. These are elementary squares or plaquettes.
I think it's just 2n.
See,
2 in?
So like in 2 dimensions, you
Well, in
have 2
3
faces,
dimensions, it was clearly
6.
6, right?
and in 2 dimensions it's 4.
1, 2, 3, 4, 5, 6.
No, but you're thinking of
So in
D
4
minus
dimensions,
1
it's
face.
bigger than
You're
6.
thinking of D
16.
minus 1, like D minus 1 dimensional faces. He's saying 2-dimensional faces.
Okay, so I was thinking he was talking about d minus 1.
Yeah, I did. Your formula is
Cross
right.
maximum is 12, it's C 4 2 mark for 2 because. Is that
Maybe it's 12.
So it would be,
No, it can't be 12. But if I divide by 2, I get 6 again.
so there, in 4 dimensions there would be 8 3-dimensional faces. If you're now wanting to find the sides of those 3-dimensional faces, there are 6 for each one. Correct? So that would be 48.
Yeah.
Anyway, your sum over all All right, to be able to say something true, I'll say you sum over all the elementary squares of the four-dimensional lattice. And these are two-dimensional squares. And in each one, the thing that you're doing is you're doing the exponential of this loop line integral, and it's path ordered. And then the limit that the squares are very tiny, that's just the field strength squared. What you want is the field strength squared integrated over four-dimensional space-time. And that gives you the partition function in four space. There's another aspect to this that's quite nice, namely, what you have, imagine that we have a field that transforms under the gauge group, and the adjoint field over here at some other point y. If you now take a path-ordered exponential of an integral from x to y of ai dxi, then you see this whole thing is gauge invariant. And the reason it's gauge invariant is what I worked out, or I don't know how much detail I worked that out last time. But the fact is that under a gauge transformation, this thing turns into u of x, psi of x, but this turns into u inverse of x, path ordered e to the x, y, ai dxi, and then this turns into psi dagger of y, u adjoint, or equivalently u inverse of y, and this turns into u of y. And so the Wilson loop transforms in this way, and so the whole thing then is gauge invariant, psi dagger of y, e to the path-ordered integral x to y, ai dxi, psi of x. I gave a sort of derivation of this last, what was it, Wednesday, I guess, but when I gave a very short lecture because I was very sick. Do you want me to go through that again, which essentially is an explanation of why it is that the Wilson loop transforms the way it does?
I mean, I guess I wasn't here, so.
You weren't here, all right, so let me get a bigger piece of chalk. Well, instead of writing u of x all the time, I'm going to write g. So I'm going to say that a prime I of x is g of x, a I of x, g inverse of x, minus di g of x, g inverse of x. And of course, you can also write that as g of x, a I of x, g inverse of x, plus g of x, So those are the two different ways. Now, the key to making this something that we can understand is the path ordering, which says that the operators or the matrices occur along the path in the order, that is to say, if along the path the points are closer to X, then they occur to the right. If they're closer to Y, they occur to the left. And it's like time ordering, but having to do with distance along the path. So if we imagine then that we've got this integral AI of X dxi, and we've made this gauge transformation, then this is a path-ordered exponential of an integral, and now it's g of x, ai of x, g inverse of x, minus di g of x, g inverse of x, dxi, and so that's what it is under a gauge transformation. This is a typo there. So, the A part is, in other words, if we didn't have any of these derivatives here, what we'd have would be a product of exponentials of GA, G inverse, dxi, one right next to the other, and the G inverse terms would just cancel, and so you just get a G at one end and a G inverse at the other end. Although actually it's, actually here, so here I may depart from this. In other words, what we can rewrite this as g of x, ai of x. If we use this form here, it's ai of x plus di of g inverse of x. So it looks like that, right? In other words, it's E. This is what the transformed thing is. And that means that we can rewrite this as e to the integral g of x ai I want to say that this is,
So you don't need the g of x inside, or g inverse of x inside the bracket, do you?
that's right, this is a,
Should just be partial I.
yeah, you're right, it's, yeah, all right, I screwed this up, hold on. Or maybe I should have left it the way it was. So this is g inverse of x, dxi, and this is a di. Right, like that. Thank you. And so this So this is, and this is G inverse of x plus dx minus G inverse of x, right?
Minus the dx.
That makes sense.
And this one is just dx. Okay, all right, this is what I want. Now, these are both of the same order of smallness. Because this has an explicit dx, and this has the dx in it somehow. And so what I'm going to say is that this little thing here, I'm going to rewrite it as a path-ordered product of e to g of x or maybe I should have had a minus dx, because I'm going backwards in a sense here. So in other words, we can sort of rewrite this that way. This term is more or less correctly represented, and this term is correctly represented to lowest order. And so this whole thing is, in fact, we can rewrite it maybe as e to the g of x, e to the ai of x dxi, e to the g inverse of x plus dx. And now we string all these things together, everything cancels except for the g of x out front and the last g inverse. But somehow I wanted I imagined that if I was subtracting more and more dx's, I'd get down to y. Maybe that's the way it is. All right, it's I don't know, I guess there's something a little missing in this derivation. What I thought we'd talk about, so there's a cute way of doing this. I'll try to work it out in time for class on Monday. What we could talk about now, we could either quit or we could talk about Michael Price's website. That's why I brought my laptop in. And what I do have is all the solutions to all the problems. And we could go through, I could show you what they look like on the computer, and that would be sort of instructive. I don't know if you want to see that.
Sounds useful.
Thank you.
What do you think?
I'd be up for that.
Yeah, sounds useful to me.
Does anybody have any question though about the lattice gauge theory?
Yeah, I get. Well, okay, so I guess one little question.
Yeah.
I mean, okay, so while maybe I don't see why this Wilson loop is something that's invariant for a general gauge theory. I mean, it's pretty easy to see why it's invariant for U1 gauge theory, right?
Why, what's invariant?
Why the Wilson loop is invariant for U1 gauge theory, right? I mean, all you get is you just get a gradient of the term, right? That's essentially all you get there. And anyway, my question is the exponential necessary for getting some gauge invariant quantity? Do we have to have the exponential or no? Or at least in the case of
That's a good question. I don't know the
one, it
answer.
doesn't seem to be necessary.
But your question actually points out that I should have worked some more on an acute way of
Yeah.
showing that the thing was gauge invariant. There is a cute way, and I don't remember it, and I forgot to work it out.
Yeah.
I suppose one way of working it out is to imagine that is to figure out how a very small Wilson line transforms, which is what I was sort of trying to do there. So in other words, if you have E to simply the AI dxi, what is this under a gauge transformation? Well, we know that it's E to the, everything's at the same, well, I was going to say everything's at the same point, but I'm about to introduce a derivative. So this is G of x AI of x, G inverse of x, and we can do it this way or the other way. If we do it the first way, then it's di G of x, G inverse of x, and it's all of this just dx. And so what we want to do is show that this is e to the g of x actually, now that I think about it, it's not so much. I think it's actually g of x, not e to the g of x. I think it's just this. But it's g inverse at x minus dx, or equivalently g of x plus dx. And, all right, here I'm remembering some of the trick. You see, this thing here, dig g inverse, this is effectively the derivative of log g.
Okay.
Because the derivative of log g is g inverse times the derivative of g. And so then what you get is a log of the ratio, and that tosses one out to one side and the other to the other side. And then this times this is essentially the same thing as that. If you forget the dx part. And so anyway, it's let's postpone that till I get you a nice derivation of it. So, do you want to, maybe we'll spend a few minutes looking at some of these solutions.
Do you think the camera should be on, or
Yeah.
it's kind of quite small?
Yeah. No.
Oh, you're right.
I can actually see the word. I can actually see
So
the
this
word.
is
Oh, no,
only
you
for
can see it.
UNM
Oh, yeah, no,
students.
he's
Okay.
got it. He's
Yeah.
got it.
Huh?
Yeah.
Yes, I can see
it
the
looks
word.
pretty good on the camera, actually.
Yeah.
Yeah, but I don't want the,
Oh, okay.
I don't want the solutions to go full part of the
Oh.
universe.
Yeah, yeah.
So why don't we just turn the thing off for today?
Okay.